Okay, welcome to class. Hope everybody had a fantastic fall break. Let me just say a few words about the midterm. Much better performance this midterm than the last. The average, I think, was a 68, so right at about 70%, where you kind of hope an average happens to land at. We still curved it up to an 80, so whatever score you see in your blue book, I think they added 13 points probably to bring the average up. So the range of scores was pretty broad, everywhere from I think a 98% all the way down to around a 10%. So basically the whole gamut. Some we almost had a perfect score and quite low and everywhere in between. Anything else I can say about that? So as always, if you feel like a problem got misgraded or something's incorrect about it, you can ask for a regrade. I'll be posting the test solutions. They're probably not posted yet. I'll post the test solutions later today. And then homework 6, that's the one for chapter that we're starting now on polymer structure and imperfections. That will be posted this Wednesday, and it will be due next Wednesday, the 24th, I think it is. So you have plenty of time on that one. Okay, that brings us to today's lecture. So we're going to finish chapter 4 today on polymers. And we're going to start on chapter 5, which is imperfections. So our objectives for the first part is to figure out, we've talked about polymers a little bit, we've talked about side groups, we've talked about molecular weight, but we haven't really described the shape of these things. I keep on referring to them as like spaghetti noodles, but we're going to talk about what exactly we mean by that. What size do they actually have when these things clump together? We're going to describe briefly the difference between a thermoplastic and a thermoset. We'll talk about different configurations and isomers and how those relate to properties. And then we'll even describe how polymers can actually be crystalline or partially crystalline. Okay? So let's start with the processing parameters that might control things like molecular weight. When you're making polymers, there's a number of different variables that you can control. One of them right off the bat that you can control is temperature. You could control the reaction temperature. You could control the amount of catalyst that you add. And remember, catalyst is the thing that kickstarts this polymerization chain reaction. So maybe turn to a neighbor and just spitball with just those two things, temperature and amount of catalyst, which ones how you might use those two factors to control whether you want a high molecular weight polymer or a low molecular weight polymer, and what might be the rationale for that. All right, what do you guys think? You got amount of catalyst and you got temperature, and you're trying to get the longest polymer possible. What do you do? Because remember, you're starting out with a bunch of little like Lego pieces, right? You're going to start snapping those together. The catalyst starts that reaction, right? So you can change how much catalyst, and you can change temperature. So what do you guys think? Yeah, you don't want it to stop. I agree.
I don't know if it'd be higher than temperature.
Higher temperature in general does what to atoms and molecules? Gives them energy so they can move around, maybe find sites that they might react with. So in general, higher temperature might be, at first glance at least, might be like a good thing. What about the amount of radicals? Or catalyst? Here's another way to think it. When you make a polymer chain, at the end of that chain is one of your radicals, right? And then it just keeps on reacting until it hits another one. So if you want as many possible long chains, do you want many or few catalysts? Or another way to think of it is every chain has two catalysts. If you react that entire batch, you want as few of them as possible. It might take longer, but by the time it completes reacting, you should have longer chains because there was fewer starting points. That's kind of the idea. Yeah, and they can. Light and things like that can break chains and then they can go, but in general, catalysts are what start and end chains. So the fewer you have of them, you do the math, by the time it's all reacted, you should have longer chains. Okay, what do people think? How do we get longer chains with the few variables that we have? Any thoughts? Yeah, what do you think?
More temperature and less catalyst.
Yeah, and I think the easiest way, can you explain why fewer catalysts will give us longer chains?
So the catalysts are on the ends of the chains, right?
Yep.
So if you have fewer catalysts, then you have fewer chains, which means more chains.
Bingo. We're assuming that we're going to let whatever our pot is full of monomers is going to keep on reacting all the way till it's done, like there's no monomers left. So if you start out technically with 2 radicals, right? 2 single bromine atoms, for example, and you let this thing keep on reacting, you would have a chain that's your entire pot, and the 2 ends would be bromine, right? In hypothetical sense, right? In reality, that's hard to achieve, right? To make it that entire chain. Plus, there's other things than just the radicals that can start this reaction, right? Light coming in can break up a molecule temporarily, right? If we go way back up to our monomers, something like this, ethylene, right? Light can come in and it can break that bond up. Light degrades polymers all the time. This is why if you have, synthetic, like in your car, right? If you had pleather seats in the back seat of your car and leave it in the sun, after a while it's all cracked and destroyed. So over time, even sunlight is breaking bonds, right? So it's not like if you add 2 bromine atoms, you're going to polymerize the entire chain, because other things can break this chain, but they're much lower in number, right? So in general, having fewer radicals will lead to longer chains. And then you said higher temperature. What's the role of temperature in this process? What do we think? Any thoughts? What's temperature doing for us? Yeah.
That changes the speed of the reaction.
Yeah, in general, that's always the case, right? Way back to Gen Chem, you remember that. If you're dissolving Kool-Aid, right? If you're dissolving Kool-Aid into cold water versus hot water, it dissolves a lot faster in that hot water. We know that as we've learned about this semester, the higher the temperature, the higher the energy of these atoms, right? And so they're able to move and rotate and diffuse through your material. So higher temperature is going to make this happen faster. I would guess if you wanted the longest chains possible, you would actually want definitely a few catalysts, but you probably don't want the reaction to go too fast. You probably want it to go a little bit slower, and you just are okay with it going longer times in order to get longer chains. So you probably actually want to cool these things. Oftentimes when you form bonds, you're giving off energy, right? And so you might want to cool this thing down during the process. But you can control these parameters, and you can control things like molecular weight, okay? If you can control things like molecular weight, you can control its properties in a pretty big way, right? Say that you've got the exact same polymer. If your molecular weight is something like 100 grams per mole, that's not a very long chain. That could be only, 1 through 10, units long. That's probably going to be a liquid, okay? Whereas if you can increase that molecular weight, say an order of magnitude to about 1,000 grams per mole, all of a sudden it's starting to look like maybe beeswax. It's a waxy solid. And if you go between 10,000 and even up to 1,000,000 grams per mole, now you've got extremely long chains and it looks like a solid. Sometimes they'll call these high polymers, right? So the things that your calculator case or your computer cases are made of, these are extremely high molecular weight because you want that additional rigidity. You want a higher melting point. You want higher stiffness. So why is it, turn to a neighbor, why is it that higher molecular weight gives you a more sturdy, robust polymer and lower weight gives you more liquid, waxy polymers? All right, you guys, what do you think? That extra molecular weight, why is it turning into a solid? Any ideas? So think of it like spaghetti noodles, right? How about this? Let's say you've got like bow tie pasta noodles versus long spaghetti noodles. You let it get cold so it kind of stick into each other a little bit. If you reach in and grab the bow ties and pull a chunk out, that's going to take some amount of effort. Now you reach in and try and grab the spaghetti noodles and pull that out, it's going to take a lot more effort. How come? Bow ties are short, so they don't tangle, right? The longer weight means longer polymer chains, which means entanglement. And entanglement, that's it's making it not deform, so it's not like a liquid, it's more like a solid. That's at least like a first glance of why it's happening. A better explanation has to do with van der Waals bonding. So ask yourself, what is it about longer polymers gives you stronger van der Waals bonding? And remember, that's not covalent or ionic bonds. Those are these weak fluctuating bonds. Why would longer chains give you better bonding? Okay? All right, what do we think? Why is it that longer chains give you more mechanically robust polymers? Harder, stiffer, higher melting point. Any thoughts? Yeah. Why? You're absolutely right. Remind us what those are, and then why do they exist in greater amounts in long chain polymers?
So what happens is there when the two molecules come next to each other that don't have hydrogen bonding or dipoles, the electrons, as they're moving, kind of create a very, very small positive negative force between the two molecules naturally. The bigger the molecule is, the more electrons there are that are interacting like that, and so those forces grow as the size of the molecules.
Yeah. Right? So even though your polymer may not even be a polar compound, meaning it's got like a big polar side group like a fluorine, you can still have a slight difference in your electron cloud. It can be slightly more on one side than the other, and that creates a slight difference in charge, and a charge difference can be related to van der Waals bonding. So longer chains just means that there's more chance for these things to be lined up and therefore have these bonds forming. If you have stronger bonds between your chains, you're definitely going to have a higher melting point, stronger polymer. But another reason why has to do with entanglement, right? If you have longer polymers, the odds of them getting tangled up gets much, much higher, right? So I teach rock climbing to scouts sometimes, and I have a bunch of old climbing ropes that I've cut into 20-foot segments, and when you grab one of those and pull on it, the odds of it being tangled is really, really low. But if I grab like a 200-foot rope and try and like grab the end and just like hope it comes out like a big long strand, it always tangles, like always, right? So it's just a function of length. So if you have longer chain polymers, the odds of them tangling and therefore not being able to be deformed is just higher, right? You have better odds, okay? So that's sort of why the same material with different molecular weights can have such drastically different properties, all the way from liquid to a rigid solid, okay? All right, now we keep on in this class, we've been drawing these things like straight lines with zigzags, right? But we keep on assuming that like it goes in one dimension, and some polymers kind of do that, especially really rigid ones like PET, nylon, Kevlar. All of these polymers tend to be quite long and aligned, but other ones don't. They actually can twist and rotate, right? So imagine this. You've got carbon bonded to another carbon, right? And we know that carbon always wants 4 bonds, so these are technically what we call tetrahedra. So if I was to draw, I'm going to draw the little triangle out thing. If you haven't seen this before, when you draw a triangle that's filled in like that, that means it's coming out towards you. So let's put a hydrogen there. And then if you see one like that with those little markings like that, that means it's going back into the plane, right? So you've got carbon and carbon and carbon forming this zigzag, but then coming out and coming in, that's where you got your hydrogens, such that this carbon in the center, that guy there, he's surrounded by a tetrahedra, right? And in a tetrahedra, what's the angle between the 4 different sides? Anybody remember this? 109.5, right? So this right here, that's going to be 109.5 degrees. And all of those angles would be, right? Now, because these aren't the same atom, hydrogen and carbon, it's going to be shifted a little bit, right? It may not be exactly 109.5. Maybe like the carbon wants the bond slightly more, or these two repel each other slightly more than the hydrogens do. So they might be shifted a little bit, but it's a pretty good estimate for the angle, okay? And then you would keep on adding these things. So if you do this many, many times, and you have this long chain, right? The question is, how long is the total length, right? If you were to stretch this thing out end to end, and I don't mean stretch it out to where you flatten out that angle. The angle's still there, but you just line it up. How long will it be, right? The way that you calculate that total chain length is going to be right here. L is going to be equal to N times D multiplied by the sine of theta over 2. And theta is 109.5 degrees. Okay, that's your theta. So you could calculate the total L. The only thing you need to figure out how long this chain might be if you were to stretch it out is N, capital N. Capital N is the number of bonds along here, right? This is just a geometry problem. All they've said is like, okay, that's a triangle. We want this side of the triangle. We don't want the hypotenuse, right? We want that bottom side. So if you know the hypotenuse, the distance between, say, a carbon and a carbon bond, which we do, it's equal to 1.54 angstroms, or 0.154 nanometers. Then you can figure out from sine of that angle divided by 2 what this distance right here would be, right? Okay? So all you need to know is how many of those chain lengths are in something. That can be figured out from the degree of polymerization. So for example, maybe do this. Let's do this one together. Let's say that for polyethylene, N equals 250, okay? It's polyethylene, which means that you have CH2 as your repeating unit, Okay? How long would this polymer be? Your repeat unit is CH2, meaning you've got carbon, it has hydrogen, and then it bonds to another one, right? And there are 250 of these. What would be the length of this polymer? Okay? Give that a shot. If you were to stretch it out, how long is it? Okay, people got answers yet? The only catch on this one with polyethylene is that sometimes people define the repeat unit of polyethylene as that. So there's actually 2 units. We'll just do the one on the left for now. I'll make it clear if it was on an exam which one I would be talking about. But some people call this one the repeat unit. We're talking about this one right here. Okay? Anybody got a length for me? How long would this be? 31.44. Nanometers? Yeah. I get 31.44 nanometers. Okay? So any questions on this? Pretty straightforward. What if I threw a twist in here, right? What if we go up to one of these other molecules? It's a little bit trickier. Yeah, like this one here. What if I asked you to do it for this molecule at the bottom, right? How would you have to modify our approach? That one's actually quite a bit harder. Let's do an easier one. Let's do this one first, right? The top one, right? That top one, you've got 5 polyethylene units, right? Then you've got a C bonded to a double bonded to an O, so a ketone unit. Then you've got an amine unit over here. What would you have to do if you were figuring out the length of that polymer? N, like lowercase n, is 250, just like before. What would you need to do to figure out the length of that total polymer? Well, let me ask you this. This carbon here at the end, it's got 2 bonds going to the oxygen. It's only ever going to have 4 bonds total. So does it still have a tetrahedral coordination? No, it's got trigonal. So now it looks like this. Like you've got the bonds coming off the ethylene thing, and then you're going to have, instead of it doing 109.5 degrees, instead it's technically going to be trigonal. It's going to be 120 degrees, right? So that would now be 120 degrees. So there are technically slight differences. We usually ignore these because we're getting ballpark estimates with this length, but to be mathematically correct, you would have to account for these angles. Or how about this one? This is a nitrogen bonded to a carbon. Is that going to be the same or different as the carbon-carbon bond? It's going to be different, right? In fact, it's probably, I think, shorter. I have to or longer. I don't think it's as strong of a bond as carbon-carbon, but I'd double check. But you could look these things up. You could look up what is the length of a carbon-nitrogen bond or a carbon-oxygen bond, or I might give you that on a homework or something, okay? Any questions on this? Okay. So that's the length of polymers. And there's some examples on YouTube where I go through this for more difficult ones in polyethylene, you can see. By the way, I know that somebody's told me that these links on the PDF aren't working, which is frustrating. That OneNote, when they export the PDF, links aren't working right now, and I can't find a way to make it work. But you can always find all of these links to the YouTube solutions on the Top Hat page, right? If you go down to the bottom of the discussion section, for every chapter, I've got all of them embedded in the thing. So in Top Hat, you can find these. All right. Okay, the other thing that can happen with the shape of polymers is they don't have to be lined up at all, right? If we had tiny microscopic tweezers and we pulled it and lined it up, it might be. But most of the time, that's not the case. Turn to your neighbor and explain why it's not usually the case that they're not usually straight, but they're rather balled up. Okay, let me pick on Andrew. What do you think? Sometimes they might be lined up, but more often than not, they're balled up into big wad balls things. Like, how come?
I would imagine that it probably has to do with different kinds of bonding happening. So some of them might be bonded with van der Waals forces, while others might be through hydrogen bonding or some other.
Yeah, that's a good point. You might have specific side groups, like if you have like an OH group, that's going to lead to hydrogen bonding, and those might seek one another out and create it to be balled up. That's one possibility. Think about it in terms of free energy in this class, right? Free energy tells us why anything happens. So is it enthalpy or entropy? You basically made an argument for enthalpy. Is there a reason why entropy might favor it as well? Any thoughts? Bonding is enthalpy. What about entropy? That's the degree of disorder. Let me ask you this, right? Every time that you've got a single bond, a carbon-carbon single bond, you've got this 109.5 degrees, but we know that single bonds can rotate. Double bonds can't. A double bond between things can't rotate. They're rigid. But if this can rotate, that means that, like, say, from going from this one to that one, as long as it's anywhere on that sort of ellipsoid, it's still 109.5 degrees. It's just rotated in some direction. So there's essentially all those different degrees of freedom. There's many, many different scenarios. There's randomness, right, that we can incorporate by having this thing rotate in all sorts of different ways. So each time that it chooses a bond, it might choose to go here, but the next one it might choose to go there. Each one has 109.5 degrees, but they can be rotated in different ways, right? And so if there is one combination that will give you a straight line, there's infinitely many other compositions that are not a straight line. And randomness is going to say, I'm going to skew towards the one where there's more disorder. Does that make sense? Why it's not common for straight line polymers. They can happen, but it's usually enthalpy dominating the entropy component. It's when bonding of some sort makes it straight, okay? So in that case, your polymer is going to wad up, and it's going to form sort of a sphere. How big is that sphere? Well, r, the radius of that sphere, is equal to d multiplied by the square root of capital N. Again, capital N, just like before, that's the total number of links in the chain. And d is just the distance of any link, right? It's like the carbon-carbon distance, okay? Are there questions on that, on estimating the size of a bunched up spherical polymer? Okay, let's keep going. Okay, so up until now we've made a lot of assumptions. We've been assuming that that first off polymers order in the same way, meaning let's say you've got something like polypropylene. Remember, polypropylene has C bonded to two hydrogens, right? And then it had C bonded to a CH3 unit and a hydrogen. That's our repeat unit for polypropylene. 3 hydrogens and 1 methyl group. But the next question is it always going to line up like that? Or will the next one in the line look like this? Right? We call this head to tail versus head to head. If they line up head to tail, then each time it's going to look the exact same. This is an example of head to head, right? If the CH3 part is the head, then they're lined up in a way that they're clumped up like that. So these are what we call configurations, okay? Configurations mean there's lots of ways you can line these things up. Head to tail, tail to tail, head to head, all these different things are possible. And then the other thing is you can actually, instead of having one long chain of these things, they can split off the side. Maybe something happened, something went slightly wrong in your polymerization, and you had a fork where something went off on the side. So you can get branched polymers, you can get cross-linking, and you can get network polymers, right? So linear is what we've been describing so far. It's like the long chain. Branched is when you've got polyethylene doing its thing, but you've got a branch of polyethylene going off the side, right? That happens. Cross-linking is when, instead of van der Waals forces holding them together, you can have permanent covalent bonds between the chains. This is how they make synthetic rubber, right? For tires, this was like one of the great innovations, that when they took regular rubber, right, and they realized that if they add just a little bit, you don't even need very much, like a few weight percent of sulfur. Sulfur, if you look at it, it likes to form 6 bonds, not 4. So if you plugged in like something that wanted 4 bonds here, like silicon, it doesn't look very different. The carbon-silicon bond is going to be different in terms of length, but it's basically the same thing. Structurally, it doesn't change very much. But if you put a sulfur there, all of a sudden that sulfur, it's got 4 bonds there, but it can have 2 more, right? So you could imagine that it could put, a bond going sort of in and out of the board as well. All right? And that's going to allow it to bond to other polymer chains or to itself. Maybe it's going to bend around itself and then bond again, right? So what that does is it takes your polymer, which was able to sort of slide past one another with more or less ease, and it still had entanglement, it still had weak van der Waals bonding, but all of a sudden you're given a strong bond, right? Breaking a sulfur-carbon bond is a strong covalent bond. That's not easy to do. So you went from having a sort of a weak rubber to a strong synthetic rubber by cross-linking, okay? And sulfur is not the only thing that can cross-link. Lots of things can cause cross-linking, but that's the main idea. You want to form strong covalent bonds. Like let's say this is my other polymer here. If these are covalent bonds linking those together, I've cross-linked it, and I've made it a much stronger polymer. We talked about network polymers already. If you remember it, they were things like bakelite. Bakelite's an example of a network polymer because it can form bonds in 3 directions, right? Not just like coming and going, but you've got this side group that forms covalent bonds. So you can think of them like a form of cross-linking, I guess, except cross-linking is only a few weight percent, meaning maybe 1 every 100 or 200 atoms is substituted for one that can cross-link, whereas a network polymer, it's all over the place. So if you were going to predict the strength of a network versus a cross-linked versus a branched polymer, you'd say that network is going to be your strongest because it has the most 3-dimensional covalent bonds, followed by cross-linked, followed by like a linear or a branched, okay? So those are what we call different configurations. There's something else we should talk about, which is isomers, right? There's isomerism. So if you've got a side group like this benzene ring hanging off the side, by the way, what is this? What polymer is this? It's got a CH2, it's got another H, and then it's got a benzene. That's styrofoam, polystyrene, right? So this is polystyrene. Now, polystyrene can exist in a couple different isomers, right? You can have isotactic. Iso means the same. Tactic must mean like the side. The same side. So if it's all on the same side, that's one way of making this polymer. Another one is syndiotactic, where it's alternating. And then you can have atactic, meaning there's no order, right? It doesn't have a side preference. So let me ask you this. Which one of those 3 will have the strongest polymer? Which one will result in the strongest polymer? Maybe turn to a neighbor and say why you think one is better than the other. Okay, what do we think? Let me pick on, I'm not sure your name, it might be Alexis, possibly. Oh, in the denim jacket. Yeah, so think about it in terms of bonding. Let's do it that way. If let's say you had like a fluorine or something on, oh gosh. Try that again. If you had a fluorine over here, not going to draw. If you had a fluorine, then it becomes a, what do you call it, a polar molecule. Then you're going to have more van der Waals forces. So if you don't have so that would make it a stronger bonded one, right? So if they're all on the same side and you have a slightly more polar or something that's going to increase the van der Waals forces, then it's going to become a stronger polymer, right? So it has to do with lining up chains and increasing your secondary bonding. And turns out when they are all on the same side, you might get like a delta negative versus a delta positive over here. They're going to create stronger van der Waals forces. They're also going to stack together closer, right? Look at this in terms of what we call steric hindrance. Steric hindrance just means like the size is too crowded. If you've got these great big things on either side or randomly distributed, that's a really big side group, this benzene ring. So it's going to push away the neighboring atom, right? But we know that force between things, Coulombic attraction, is equal to K, Q1, Q2 over R squared. So if you bring things closer together, it's a stronger force holding them, right? And so steric hindrance is another reason why it might be a weaker bond. So if you want a stronger polymer, you'd actually like an isotactic polymer. You'd want them all on the same side. Are there any questions about that? Okay, let's keep going. All right, the last thing we'll talk about with this is geometric isomerism. So if you've got something like this, remember this is our polyethylene molecule. Well, when this is a monomer right now, because it's got a double bond, right? And across that double bond, you can choose to have the functional group both on the bottom side, or you could have it on opposite sides. So this is cis versus trans, and it's another way that you can have disorder in your structure. Whether it's random in how it has cis versus trans, or if they're all cis or all trans, whatever, you can figure that out, okay? All right, let's talk about thermoplastics versus thermosets. Thermoplastics, the general rule, these things get soft when you heat them up, which is good for some things. It means that they're more easily recycled. It means that they're more easily shape-formed in the first place because you can just heat it up and injection mold it. Injection molding is the process of you have a cavity that's the shape of your final product and you squirt in the hot material, it cools down and it has the shape. So when they make the vast majority of everything out of plastic, it's injection molded because it's extremely low cost, right? You have a die with lots of little side channels, you squirt your main polymer down the main channel and it just goes off to the side channels and you can make hundreds or thousands of things at a time. It's a great way to process things, but it works well with thermoplastics. It doesn't work as well with thermosets. It can, right? Thermosets, instead, these things become hard upon heating. You heat them up and they actually get harder and harder and then they burn. So instead of melting and flowing, they burn. So it doesn't mean that you can't injection mold thermosets, but it means that you have to injection mold it and then thermoset it. The reason that they form these hard bonds that have to be broken because they form covalent crosslinks. So essentially, if you do injection molding of a thermoset like epoxy, then you need to inject it first and then cross-link it, right? Which they can do. You can do that with light or with heat. So you inject the two parts of it like a two-part epoxy. If you do it quickly enough, it can flow, and then you let it set, and now it's rigid and it can't be melted again. Yeah, Ashton?
So the process of heating it up, does that add more cross-links, which why it gets harder? Like more things are bonding between?
Yeah, that's typically what happens. There's some other things that can happen. You can dehydrate them. Sometimes these are hydrated, and so as you pull out water, that can structurally change the molecules as well. But that's the idea. So that's the key difference. If it melts, thermoplastic. If it would burn, that's a thermoset. Thermosets and thermoplastics both have their place. Both are important. Epoxies are incredibly important, but they're almost all thermosets. They're much stronger, but you can't recycle them, right? If you're trying to recycle epoxy, it's much, much harder because you have to like dissolve it, right? Whereas thermoplastics, you can just melt it, which makes them much easier to recycle, okay? We already talked about copolymers, but if you have something that repeats every single time, if you remember like nylon 6,6, the 6,6 part of nylon, if we go way back to before fall break, I think I just passed it. Yeah, nylon 6,6, it sort of had two groups. It had this monomer and then it had this one, and they alternate like AB, AB. But we said that there's other ways to make things alternate. They don't have to be AB, AB. They can be random. They can be blocks. You can have a big block of one monomer and then a big block of another one. And this flexibility allows us to make just incredible things with polymers. It adds so much design space for designing new materials. You can have it so like A is all along the main chain, but you've got B for your branches. That's another possibility. Just lots and lots of possibilities when it comes to copolymers, okay? And you use these all the time. If you've ever heard of like SBR, styrene butadiene rubber, right? Or like acrylonitrile butadiene rubber. These things have all to do with different block copolymers. That's what the different names are, styrene butadiene, right? Okay, talked about polymer crystallinity a little bit. Polymers, we've said that they can line up, right? And in the simple picture, I've just been drawing it like this. Like you've got a long chain and another long chain next to it, and that these things can bond a little bit between them. In the real world, we said that polymers don't usually line up all the way. So instead, we sort of settle, we meet in the middle, and this is what it looks like. You get regions of lining up and regions that aren't lined up. So you might have region like that that's lined up well, and then this does something else, and it gets amorphous, and this one does something else, but you have another one that sort of fits in here. So you've got these amorphous regions in between there that don't line up very well, and you've got regions that are crystalline. And it doesn't have to be like it's completely crystalline or completely amorphous. You can have some fraction of both in your polymer, right? Now, the question here, this is our clicker activity. I can pull it up. So start thinking, what would you expect? A higher density, higher or lower density for a crystalline or amorphous polymer? Which one would give you which? Density in terms of just how heavy the thing is for a given volume. Okay. Would you expect higher? Oh, that's a poorly phrased question. I will fix this after class, but I think it's supposed to be which one's higher. Which one would have a higher density, crystalline or amorphous? Which would have a higher density, crystalline or amorphous? I need to fix that question. Is that even working? I feel like I'm shouting. Is it even going through the speakers? Again, we're asking which one's a higher density. Sorry for the poorly phrased question. Higher density, crystalline, amorphous. Get your answers in. Okay, we're going to wrap it up. Okay, right. So most people think crystalline. That's the right answer here. So why is it that crystalline is able to be a higher density polymer? What do we think? Yeah, Ashton? Yeah, isomers.
They're all lined up on one side. For the other side, they can line up with each other much easier. It's like putting all your clothes in the box or folding it and putting it in the box.
Yep, that's exactly it, right? So the crystalline regions, they're stacked together as close as they can. They're going to be higher density. We know that there's wasted space in the amorphous region, so that's going to bring your density down. Because of that, and this is pretty remarkable, you can actually calculate with pretty good accuracy the percent crystallinity from the density, right? So let's say you wanted to figure out the percent crystalline. I want to know, is my polymer 50% crystalline or 100 or what? If you know what the density of the purely crystalline part would be, and you know what the density of the amorphous region is, rho A, and you measure the density of your sample, it's a simple geometric expression to figure out what the percent crystallinity of your sample would be, right? So I think it's surprising that this works at all, but this is actually a pretty good proxy for how crystalline your polymer is just by measuring the density. Now you have to know ahead of time the density of it in a fully crystalline state, which something like X-ray diffraction can tell us, and you have to know it in the amorphous state, and that's harder. Some of these are tabulated. I think actually Danny had to figure this out recently on a project we did. Where did you find it? In the literature somewhere?
Yeah, they had it listed in some stuff.
Yeah. So you can find it oftentimes in published literature or somewhere. Okay? Any questions on crystallinity, amorphous versus crystalline polymers? Any questions? There's some general rules of thumb. If you want to increase the crystallinity of your polymer, you might try cooling it very slowly. So you're going to heat it up to a melt, and then you're going to cool it very slowly. And by doing that, you're going to give it as much time and thermal energy as possible for these chains to find regions that they can line up next to and bond. If you quench it quickly, you're more likely to get an amorphous polymer. Cooling it slowly, just like with ceramics or metals, you're more likely to get crystalline rather than amorphous if you cool it slowly. Okay? Although some simple structures like PE or PTFE, Teflon, these things crystallize kind of no matter what you do to it. Even if you quench it rapidly, it's tough to prevent crystallization because they're such simple structures. If they have big side groups, it's harder and harder to crystallize. Yeah, Ashton? And then other question?
What is a rho S?
So rho is density, and then the subscript C, S, and A stand for perfectly crystalline, your sample, and amorphous. So if you can measure the density of your sample, that's rho S. By the way, thank you for asking that question. If there's ever a variable that I haven't properly told you what it is, just ask for the clarification. I remember that was a big pet peeve of mine when I was a student, like, I don't know what those letters are. So please ask me to clarify. I appreciate it. It goes without saying, if you cross-linked your polymer, the odds of it being crystalline go down, right? Because now you've imagine you start out with a bowl of spaghetti noodles, right? That were cooked, so they're all over the place, and then you drizzle super glue over it. Your ability now to line those things up is kind of broken because you glued sections of them together. So you're going to make it much more amorphous if you do something like cross-linking or forming a network polymer. And adding big side groups, the same reason. It makes them hard for them to line up, so they're harder to crystallize. Okay. You can actually do X-ray diffraction for polymers the exact same way that we did it for ceramics and metals, right? You figure out the volume of the unit cell. You figure out how many repeat units of your polymer are in that cell. you could figure out a d-spacing, right? Just like we've done before, you can do diffraction on polymers. Not all polymers will see an X-ray diffraction pattern. XRD polymer. It's more often than not that they don't have strong reflections. In fact, you'll see something like, oh, perfect. Okay, so if you take a look at this, here we've got a crystalline and an amorphous version of a polymer, right? The pink one, for those that are colorblind, that's this one. It's got this broad amorphous, we call it peak. And then the crystalline version has like strong, like these sharp peaks at certain spots. So in an amorphous material, you don't have nice long-range order. You just have like average distances between atoms, but you don't have nice planes of atoms. And so you don't see a sharp peak which corresponds to a single plane. Instead, you just see like an average distance of molecules. So the location of this peak tells you something about the average distance of atoms, but it doesn't give you like a nice peak and therefore a nice d-spacing, whereas the crystalline version's got really nice d-spacings. Okay? So it's very common if you do diffraction of a polymer to see a big, broad, what we call amorphous background, and then you might see a few peaks on top of that. And that means that you've got a material that's neither completely crystalline nor amorphous. It's got a little bit of both, right? And there's ways to refine out how much is crystalline versus amorphous from diffraction patterns, but we're not going to cover it in this class. Okay? So again, one more time, you don't have pure one or the other. You've got regions of amorphous behavior, and you've got regions of crystalline behavior in like these blocks. Okay? Any questions before we finish this chapter and move on to imperfections? Any questions about polymers I haven't covered well enough that you'd like more explanation on? Okay, we'll just get started on chapter 5 today. We won't get too far. Okay, our objectives are, you know what, we're probably just going to cover vacancies versus interstitials, and we might talk about Schottky versus Frankel defects. That's probably all we'll get to today. So in this class so far, we started out with bonding. We moved to free energy. Once we understood bonding, we then introduced entropy. We said, okay, it's not just bonding, it's entropy that matters. From there, we could then say what phase diagrams were. We had these map of telling where the different phases existed. We then figured out what in the world phases were, right, in terms of crystal structure or polymer structure. We're now ready, up until now, everything's sort of been like perfect scenarios. We're now ready to start introducing disorder. What happens if something's not perfect, right? If atoms are missing or out of place? What does that do to your properties? What does it do to all sorts of things about it, right? So let's dive into that. To do so, we're going to start by talking about zero-dimensional or 0D point defects. So these are point defects that happen at exactly one point in your crystal. That's not a defect, for example, that continues in a line or a plane or a three-dimensional like a void. Those are different types of defects. We're going to start with just 0D, okay? And the two common ones that we're going to talk about in this class, there are others, it's vacancies and self-interstitials, right? These are the most common. So a vacancy, it's just a vacant lattice site. You would normally expect an atom to be there, a metal or something, but it's not there, right? And all crystalline materials have vacancies. They don't all have them to the same amount though, right? So maybe turn to a neighbor and talk about, in terms of driving forces, what drives vacancy formation, and then what prevents vacancy formation. Turn to a neighbor and discuss this. Okay, the first one, what drives vacancy formation? Is it A, entropy, B, enthalpy, C, I can't remember what entropy and enthalpy are, or D, I don't care about vacancies? A or B? How many D's will we get? 10? 10 or less? What's the over-under? What's the over-under? 3? Okay, get your answers in. What drives the formation of vacancies? We're going to close the poll. Okay, answers in. Driving vacancies is what? Okay. Entropy, again, with the same ratio as our last question. So consistently, like 80% of people are getting it right today, right? Entropy is driving it. Entropy is disorder. So somebody who voted entropy, help me understand, how is disorder increased with a vacancy? Anybody want to try to explain it? Everyone's feeling shy today. Can I pick on Claire? Claire's looking like she doesn't want to be called on.
Well, okay. So if it's not symmetrical
Uh-huh.
and it's random, it's harder to match them up evenly because there's no vacancies.
Yeah. Think of like a car parking lot that's filled with cars, right? If there's a car in every single spot, how many ways are there to arrange cars in spots, right? If all the cars are identical, there's one way, precisely one way. And if the parking lot's empty, how many ways are there to arrange it? Just one, because there's no cars in any of the spots, right? But everywhere in between, you start to introduce lots of variability. What if there's one empty spot? Well, that one empty spot can be in any one of those empty spots, right? So if there's 20 spots, that has some degree of randomness associated with it, right? In fact, when would you maximize entropy? When would you maximize entropy? Yeah. Yeah, when that parking lot is half full, you maximize the configurational entropy. Configuration is just number of ways of arranging things. If the cars are all identical and you can't tell them apart, 50% would be maximizing entropy. So that leads us to our next question. If entropy is, and it does, dominate why vacancies are formed, why isn't it the case that every single crystal, right, the aluminum in this pen, why is it not 50% filled and 50% vacant? Right? Let's go to our next question. What prevents vacancy formation? This should be pretty straightforward. Is it A, entropy, B, enthalpy, C, broken bonds, or D, strain? There might be two right answers here. I don't remember when I programmed this. I get the feeling like there's two right answers. Okay, get your answers in. We're going to wrap up the poll. Okay, we're closing it. Okay, people think, yeah, B or C are the right answer here, right? The thing that prevents vacancy formation, if we just said that if entropy had its druthers, half of the atoms would be empty, and that's not the case. So what's preventing that is enthalpy. It's that things want to form bonds, right? They want to form bonds, and if you take out an atom, like if I pull Kayla out of her seat, right, then the 4 students that were next to her are all going to say like, oh, we had a bond going on there, right? And now it's gone. And that made everyone sad in the vicinity of Kayla, right? So that's driving against entropy, right? So you have enthalpy. Broken bonds and enthalpy, same thing, right? The same thing. So both of those would have been worth credit, I hope. Okay? So that said, we know kind of the reason why vacancies form. Yeah, Ashton?
I just wondered, this is a question I had in mind a little while ago. And that's the same reason why you can't have an infinite chain of carbons. Is a similar reason because entropy dictates that things are broken up into smaller pieces?
Yeah, if you have one long chain that has some degree of entropy in it, or if you break that into 5 moderate length chains, they can be arranged in many more ways. So entropy is driving them to break apart, yeah. So it's always a balance in this class. Everything we do, free energy drives everything, and free energy is a balance between entropy and enthalpy, and we'll pick up here next time.